Ladies and gentlemen, welcome. Here we go. We are going to do a next video of section 4, and that title of the section is Secants and Tangents. And I just did a video on the secant and tangent basics, what a secant is, what a tangent is, what it looks like, the definition. And we're going to extend that a little bit in this particular video and talk about a common tangent procedure. But here's the essential question you need to write in your notes. How do you find the length, that's the question, of a common internal tangent or a common external tangent? And we're not talking common tangent circles, whether they're internal or external. We talked about that in the last video. This is a tangent line that is tangent to two different circles, and there's one called internal and one called external. And there is a step-by-step procedure. It's, I don't know, 5-6 steps in that range. It's out of the book, but I'm going to put it in here in this video, and you need to write down each step word for word. I'm going to do this example that's behind me for you guys so you can see how the steps work out, and we'll apply it to many other examples. But no matter what, this is what I love about the procedure. Whether it's an internal tangent or external tangent, it will work exactly the same. The external tangent one is a little easier sometimes than the internal tangent, but guess what? I'm here to tell you the procedure is exactly the same, and you'll get the right answer if followed properly. So I'm excited to show you that. So let's at least do this. Let me give you a couple pictures and I guess a verbal definition of what internal tangent is and external tangent. So draw some circles in your notes, and let's do that right now. Okay, so you see on your screen two different circles that's drawn here, and the heading says common tangents, and we got common external tangents, and we got common internal tangents. Now, just so you know, this is a circle. If I put that circle like that right there, like the one that's over my shoulder, you can see it. These guys are called common externally tangent circles. Yeah, because remember, intersecting right there at that one little point. Wonderful, but the circle is outside the other one. If I pull the circle inside of it like this, they're commonly internally tangent circles. Common internal tangent circles like that. But we're not talking about that in this video. What we're talking about are these things called common external tangents and common internal tangents. Here's your first one that I draw. So there's an example of a common external tangent line. It is a line that is tangent to two different circles. Notice the circles are different sizes, but truth be told, it doesn't matter. There's two different points of contact, one right there and one right there. That is a common external tangent. Now, just so you know, this procedure, this video that we're talking about, is actually going to help you every single time find the length of that common external tangent. Not the whole line. You can't find the whole line. But just from that point of contact to that point of contact, you're going to be able to find it. And if I drew the other one, here's the other common external tangent. So those are an example of a common external tangent. They don't go between the two circles. They stay on the outside of the two circles. A good way to talk about it. And there's also things called common internal tangent lines, like these. So as you notice, that point is the point of contact. That point is the point of contact of the other two circles. Again, it doesn't matter the size of the circles. One could be smaller, one could be bigger, but that's still a common internal tangent. And again, this procedure is going to help you find from this point to this point the length from those two guys right there. That's what we're talking about again in this video. Now, is there another common internal tangent? Sure. It goes the other way. Ding, it looks like this. So those blue ones are common internal tangents, and the red ones are common external tangents. So let's go do an example, get some notes, get this procedure down of finding the length of one of these common tangent things that we're talking about. So let's go do it. Let's get an example. So the example that needs to go in your notes is this one right here, and it says this. A circle with a radius of 8 centimeters is externally tangent, like the one behind me, externally tangent to another circle with a radius of 18. The question is, find the length of the thing called a common external tangent. Now don't get confused. We see externally tangent here. That's talking about the circles. Again, look at the video. That's these two guys. They're circles. But this green thing, guys, that's the common external tangent line. That's what we're trying to find the length of. Not the line itself again, but just from A, that point of contact, to B, that point of contact. And one circle has a radius of 8. The other circle has a radius of 18. I will tell you tremendously from the bottom of my heart, please make sure you do what you can to draw accurate pictures. It will help you tremendously in getting the answer correct and seeing these procedures of this step-by-step thing even work out right. So please make sure your pictures are somewhat accurate. Okay? Let's rock and roll. Let's do this. So, step number 1, I would title your procedure Common Tangent Procedure. Notice, again, it doesn't say Common External Tangent Procedure or Common Internal Tangent Procedure. Why, Mr. Motter? Because it doesn't matter which one it is, external, internal, this procedure still works. So here is step number 1. You need to draw a segment joining the centers of the two circles. Now, it might already be drawn for you. In this example I'm doing behind me, it is not drawn. So let me draw it. You should too. So between the centers of the two circles, I'm going to draw, let me draw a different with blue. Where's blue? Here we go. I like blue. So between the centers of the two circles, I'm drawing a line that connects those two things right there. So let's label it, I don't know why, but let's label it, that's C and that's D. Wonderful. Okay? That is step number 1. Step number 2, draw the radii to the points of contact. Now again, please make sure your pictures are accurate as much as you possibly can. I'm not saying they have to be perfect circles, but make them pretty darn close because this helps tremendously. So, when you draw the radii to the points of contact, that means from center C, I'm going up to that point of contact, exactly like that, guys. And then from this center to that point of contact, I'm going to draw it like that. Here's the scoop. Notice this. We'll talk about it, but notice these two radii are they appear to be parallel. Are they parallel? Well, we'll get to that in a little bit, but notice that is how I'm talking about being an accurate picture drawer. Make them look like that. If they're not parallel, something's going on, something weird. So that's step 2. Step 3. Through this is the most important one. If you could star one, star this. But through the center of the smaller circle, draw a line that's parallel to the common tangent, whether it's internal or external. This one happens to be external. So through the center, I'm going to use a red line for that. And now I'll use a black one just so you can see it. So through the center of the smaller circle, that's this one, through this center right here, I have to draw a line that's parallel to the common external tangent. That's this, the green line. So somehow I have to draw one that is somewhat parallel. There we go. To the green line. It's pretty close. Let me extend it over here. Not that it matters so much. So I'm making this parallel to that. Perfect. So if you need to use a straight edge, a ruler, or side of your book, side of your notebook, do it. But that right there is parallel to my common tangent. Whoa. Here's why step 3 is important, because you might be able to see it. Notice what that creates, though. This is step 4. This line will actually intersect with the radius of the larger circle. And it did, right over here. I'll call that point E. So it intersected over there with the other circle. And notice this in your notes here on the video. It says extended if necessary. Sometimes you're going to see in class when we do some examples, you're going to have to extend this particular radius a little bit more to make it connect. I might show you a picture of that depending on the length of this video. But in this example, it does intersect right there at point E. And then it says, notice though, it forms, as it says down here, to form a rectangle and a right triangle. Now you say, how is that possible? Well, check this out. Remember, we talked about this in the last video. A radius drawn to the point of contact is always, you should fill in the blank right there, perpendicular to that tangent line. Same thing over here. A radius drawn to the point of contact is always perpendicular. So we got ourselves right angles. Now check this out. We got parallel lines that I just created. We know parallel lines means interior angles on the same side are sup, which makes these guys beep, also a right angle. Lovely. That means this is a right angle. So what does that mean? That means from A to B to E to C, you got it. That is a rectangle. Yeah. And notice what it says down here. Again, look back in your screen. Right triangle. Actually, you're already looking at your screen. Never mind. I'm looking at the screen. It says right triangle. Well, here's where the right triangle is. If that's 90 degrees, that bad boy right there is going to be 90 degrees. So, bada bing, woo, we got ourselves a right triangle. C-E-D, deck, said, whatever. That is a right triangle. So, once that is done, ladies and gentlemen, man, your answer is going to come like that, because all we have to do is now apply the properties of rectangle and apply the properties of right triangles. Principal reduced triangle could work, Pythagorean theorem, Pythagorean triples, all that stuff, and it's going to help us get our answer. Watch how cool this comes together. By the way, there's your step 5. Use the Pythagorean theorem and the properties of a rectangle. Let's do it. So what you're going to see is these. Okay, so you're looking at this screen now, just the screen, just with this picture behind me. So you're going to see, if I got some lengths here, let me write this in. Oh yeah, I do. Let me get the red marker. So I got this little radius over here is 8. I should have put that on to begin with. It's okay though. I got this whole thing from B down to D. That thing is actually 18. Now, here's what's cool. Observe, if this is a rectangle, which it is, that means from A to C, if that is 8, that means over here from B to E is also 8. Use different colors so you can see this. Well, I'm putting all kinds of colors on here. So that means this piece right here, I'll erase this, that piece has to be 8, which means that that little piece is 8. Hold on. The whole thing from B to D is 18. But if that's 8, that means this piece, boy, this isn't drawn to scale. See, even me, I didn't quite draw it to scale, but it still looks nice. That's right. This little piece here is 10. Lovely. So the whole thing is 18. I found that to be 8 again because that over there is 8. So therefore, rectangle means the opposite sides are equal. So therefore, that little piece is 10. So how do I finish this? How do I find the length up here from A to B? Well, let's use the right triangle now. If I notice and observe, since I know the circles are externally tangent, from here, that point, you can see it, over to C is nothing more than the radius of the smaller circle. So therefore, that has to be 8. Oh yeah. So from here, the point of contact of the two externally tangent circles, over to D is nothing more than the radius length of that one, which means it's 18. Oh baby, which means this whole thing right there then has to be 26. Boy, this picture is getting really cool. So what does that mean now? If I redrew the triangle from C, E to D right down here, C, right angle over here, this is C, this is E, this is D, that's my right angle. That piece right there is 10. This whole thing right there is 26. Well, I can definitely use the Pythagorean theorem, no doubt. But I see that I have 10 as one side. I don't know the other side. We'll make it x. And I know the hypotenuse across from 90 is 26. Well, you might know right off the top of your head, but if we do the principal reduced triangle and we divide everything by 2, divide by 2, divide by 2, that means this one has to be 5. This one is still x over 2, so I've got to make sure I convert that back. And that's 13. Bam! What is it? 5, 12, 13. You got it. So that means if I convert it back, that means this is 24. Back to the picture. If that's 24, that means from C to E is 24. I'll erase that, which means that's 24. Oh, that means properties of rectangle. From C to E, that distance from C to E is the same thing as what it is from A to B. The 2 points of contact, which is what? Oh yeah, is what I needed. So that means up here, that answer and that distance is 24. And ladies and gentlemen, good job of doing your first common external tangent. I'm so proud of you. So back to the procedure, back to the steps to make sure we can recap that. So there they are, common tangent procedure. Draw the segment joining the centers. Draw the radii to the points of contact, and through the center of the smaller circle, you draw a line that's parallel to the common tangent. Again, your picture needs to be drawn as accurate as possible because all this coming together is extremely crucial to look right, to make a rectangle and a right triangle. Excited to try these in class? Not try. We don't try things, guys. We do not try. We do and we master. I'm excited to see you guys in class when we do this. See you there. Later.